Live, we're good to go. Okay, hello everybody. This is the very last lecture. This is the grand finale, and we're gonna, we're gonna take a little bit of a different lecture today. Today, what I want to do in the first half is give you a master recap of pretty much everything that we've learned so far. So we're gonna go through almost from day one all the way to the end. Again, just to give you a sense of a revision, but also maybe give you some overview of what you've learned. And then in the second half, again, depending on how we do on time, I want to look ahead. I want to introduce, or at least start um, a discussion on how to go beyond what we've done in this lecture course. Right? In particular, what can you expect from a course like 4041? But also, how does this theory that we've seen, Maxwell's theory, which is, like about 150, 200 years old, how has it evolved since? Okay. And so in particular, we're going to take a look at, how do we transition this into something like special relativity, which is a precursor of general relativity, but also, how would we, how would we merge this with quantum mechanics? And in particular, how do we, treat something like quantum electrodynamics? Okay, so that's for the latter half. But let's first just, do an introduction first. Okay, in that case, let's get started. So, as I was saying, we start with a big recap. Okay, now I'm not going to go through all the details. This is really supposed to be just a summary. If these concepts are not familiar, then please do go back to the videos, go back to the notes and take a look. Okay, so excuse me. So the first thing that we really did was to look at Coulomb's law, right? So we looked at Coulomb's law, and in particular what it says about the force between, let's say, particle 1 and 2, which we know is just a constant, and it's proportional to the charge on the first and the second one, and then the distance between the first and the second one squared, again in the direction that links the first one to the second. Okay, and so the last term here is just the directionality, right, as a unit vector. Now, as I was saying, when we go from 2041 really into 3041, the thinking is taking a slight shift, right? Instead of thinking about forces and how particles behave, the motion of particles, instead we really much focus on the fields instead. And so rather than taking, Coulomb's law approach, we look at instead the electric field, right, that you can derive from this. So the electric field is simply defined as, the limit that we take the charge on which is being acted upon. We take that to we take that to 0, and then it's that of the force like this. Okay, 1, 2. Sorry, divided by Q. So okay, so what we're really looking at is trying to take out the test charge that we have, and consider that when we have a single charge that produces an electric field, that when you put another charge there, you can you can treat that as a force, but only when there is that other charge present. Okay, and so we considered the principle of superposition, which basically states that the influence of one charge onto another is independent of all the charges surrounding it. Right, so we have that the interaction between charges are independent of the surrounding charges. And this really allows us to, construct whole densities, right? Charge densities in terms of single charges first. So, for example, I can write that the electric field as a function of the R is just given by the sum of I1 starting to N, so then dq I divided by, in this case, R minus Ri, and then R minus R over R minus Ri here. Okay, and so in this case, oops, okay, so in this case here, this then allows us to write this in also in a continuous form. So here, what we do instead is just, we take this sum to almost be a Riemann sum, and then we write dq. This is R minus R prime squared R minus R prime over R minus R prime, like this, where in this case dq is simply either given by the charge density times some volume element, surface density times some surface element, or just some line density and the line element. Okay, now similarly, we can consider from Ampere's experiment. We can deduce what the magnetic field is. This simply gives us F12 minus Km. Okay, this is a different constant. And so for straight wires, it's just I1, I2, L divided by R2 minus R1, R2 minus R1 over R2 minus R1. Okay, so and by taking a closer look, we can actually arrive at the so-called Biot-Savart law, which states that B over due to a small current element is just dl cross R minus R prime divided by R minus R prime cubed. Okay, so in this case, we can assume superposition in such a way that B can be written as the integral of all these small elements. Because again, superposition merely tells us that the surrounding doesn't matter. Okay, so we have these two fields defined now, and that's more or less where 2041 then states, okay, well, now we can do basic calculations. We've got them in integral forms, right? We can sum up all these small little elements of the electric field, the magnetic field, and that's it. But the onset of this course is really to take a look at fields, okay, vector fields, scalar fields, and so what we first looked at was so-called Helmholtz theorem, and this really states under what conditions a field is fully specified. And in particular, Helmholtz theorem says any vector field, let's call it F, can be expressed as in the following form. So F is just minus the negative gradient of phi times the curl of A, in which case phi is a scalar field, is a scalar, let's call this a scalar function of R. A is a vector function of R. And this is important, if the divergence of A is a specified function of R. Now, there is an important, corollary. I can't even talk anymore. Corollary to this, and that is not only that we can write any scalar field, any vector field as a negative gradient and as a curl, but also, and this is also important, it also means that if the divergence and curl are known, then the vector field is fully specified. Okay. Now, of course, the caveat is that this is what we said before, provided that the divergence of A is specified. Okay, now, in this case, the divergence in the curl of the electric field and the magnetic field are exactly, just Maxwell's equations. And so, indeed, in the quest for us to understand, okay, how can we specify the electric field and the magnetic field, we very naturally arrive at Maxwell's equations. And so Maxwell's equations, in this case, for static fields, are simply given by the divergence of E is rho epsilon naught, the curl of E is 0, the divergence of B equals to 0, and the curl of B equals mu naught J. Okay, now this should be supplemented with a statement about conservation of charge. So this is charge conservation. And all this is saying is that the divergence of J is 0, meaning that there's no net charges going in or out. Now, conversely, okay, so this is the this stems from Helmholtz theorem if you specify these four, but it also means that E can be written as a negative gradient, right? Just a negative gradient, and B can be written as the curl of A, where in this case phi and A is the scalar potential and the vector potential of this field. And these two together, okay, so these two then satisfy the Laplace equation, or sorry, the Poisson equation, where the Laplacian of phi is negative rho epsilon naught, and the Laplacian of A is minus mu naught J, like this. And in this case, in order to go from here to here, we have made the explicit assumption that the divergence of A equals 0. Right? And Helmholtz theorem indeed tells us that we do need to fully specify the divergence of A. Okay, now this is also called a gauge, and this will be very important when you start doing more advanced applications as well. The choice of gauge is going to be important. Okay, now this is a little bit the opposite direction in which we've taken. All right, we typically start with, especially in 2041, you start with the integral form. Here we started with the differential form, but nevertheless you can switch between those two by realizing two fundamental theorems. So we've got Gauss's theorem, which allows me to write that the integral of the divergence over some volume equals to the integral of just the E times ds, where ds here is just the bounding surface of the volume here denoted by tau. Similarly, we can consider Stokes' theorem, which is analogous, but now instead we have that the curl of E integrated along some surface equals E dot dl. Here, in this case, dl is just a line element, and the full integral is just this is the line element that bounds the surface A. And so by using these two theorems, we can write our equations in in an integral form. So for example, we get a E dot ds equals to 1 over epsilon naught integral rho dv, okay, which merely states that this is the total enclosed charge. We have that E dot dl equals 0. Okay, that comes from the curl, and we have that B dot ds equals 0, and we have that B dot dl equals to mu naught integral of charge dA. Okay, and so this is the total charge here, this term here. And again, we supplement this with charge conservation, which simply states that J dot ds equals to 0. Oh dear. Oops. Should usually. Did I do that right? No, that's not right. The curl is that is should be I, yeah. Wait, did I make a silly mistake here? Getting myself confused now. B, let's see. The curl of B is that. Yeah, okay, there should be an A. Yes. Okay, this is correct. Okay, so and we also have that the potentials are now given by the pen stopped working. That's just awesome. Okay. Okay, let me try to fix this. The pen is suddenly not working anymore. Come on. Okay, here we go. Okay. Now we can write the potentials in the following form. It's KE integral of rho r minus r prime dv, and similarly A equals Km integral J r minus r prime dv prime. Okay, in this case, again, prime is just the coordinate system that takes into account the inside of the source, and then r is the position from the point you're considering all the way to, to that element of the source. Hello? Sorry, 1 second. Okay, sorry about that. There's someone at the door. Right, this is the potential. And so the next thing that we have, now that we have the whole set of Maxwell's equations, the next set is, of course, is to ask, okay, well, how can we solve this? Okay, and that's something that we looked at in quite a lot of detail. And in particular, we were tasked to solve either the Laplace equation, which has no source, or the Poisson equation, which has a source. And so just by looking at this, more specifically, if you look at this equation here and this equation here, we see two Laplace equations, which are second order partial differential equations. And we've seen that the solutions depend on the boundary conditions. Okay, and in particular for this particular PDE, what we have is we either need to specify the so-called Dirichlet condition. So this is the Dirichlet condition, which says that the value kind of well, let's not specify the value of the function of interest is specified at each point. Again, we do mean on the boundary. Or so-called Neumann conditions. The Neumann condition, which states that the value of the derivative is specified at each point. Now, for for the electric and magnetic fields, especially given Maxwell's equations, are given by the following. So we've got that in the boundary of the two spaces, that the electric field is discontinuous in the following way. So it's discontinuous in the perpendicular sense to the surface. Okay, and we have that B2 minus B1 equals mu K cross M hat, where sigma is the surface charge density and K is the surface current density. In this case, phi and A, so the potentials are fully continuous. So this is how we can analyze this class of equations. Now we've seen that that a particularly useful tool is a so-called uniqueness theorem. So this is actually stating whether solutions are unique. And I'm simply paraphrasing. This is not the mathematically rigorous description, but very loosely, if it says that the solutions that satisfy the Poisson equation or Laplace equation with the appropriate boundary conditions are unique. And I underline unique because what does that mean? Well, it means simply that if, for whatever reason, you're able to find a solution that solves the Poisson equation or the Laplace equation, and that fits the boundary condition, then you're actually guaranteed that that is the unique solution. And so, one thing that then immediately derives from this is the so-called method of images. Where, very simply put, we can introduce so-called images outside, again, conscious enough, it's outside the region of interest. outside region of interest to satisfy the boundary conditions. Okay, now what does this do? Well, it means that if I'm able to use, let's say, an image charge, if I have an infinite plane and I've got one thing here and then there's a conducting wall in between, then that solution is the same as if I put another charge at some distance away from it. Because if I can make the boundary condition satisfy, which in this case for a conducting layer is simply stating that, or grounded conductor is simply stating that it's zero, the potential, and I can achieve that by just having an exact image charge in the opposite side of the wall. So once I've been able to specify this, then I know this is the unique solution. Now another useful method is the so-called multi-pole expansion. Multi-pole expansion. And this is the starting point is here is that the particular solution to the Poisson equation is simply given by either phi equals ke integral of rho r minus r prime dv prime or a equals to km integral j divided by r minus r prime dv prime. And so instead of calculating this full expression, we can use the multiple expansion to so-called approximate this by some series. This is simply 1 over r, and we get the sum of n from 0 to infinity of r to the power n, and r prime to the power n here, and then this Pn as a function of cosine theta, where in this case this Pn are the so-called Legendre polynomials. Okay, so we've got this expansion, which then also means that I can write phi if I only take the first few terms. So that's ke, and then I've got q, big Q over r. I'll define these in a moment, and then we get r dotted with p cubed and the rest. First order q is simply the integral of rho dv. Okay, prime in this case, and actually it's a little bit more explicit. Rho is a function of r prime dv prime here, and similarly p equals to integral rho dash, and we get rho as a function of rho prime dv prime. Now we can do the same thing for the vector potential, which at least to the first order is just n cross r divided by let's see, r cubed in this case. Okay, now in this case the first term, the q, or the equivalent of q, disappears. It doesn't exist actually. Okay, I should really stress that this is just the first term. Okay, and the final method that we looked at in this case is the so-called separation of variables. Separation of variables. In this case, our assumption is that this function, so let function u be separable and so I can write u x y z. It's just big X x, big Y y, big Z z. Now that's Cartesian coordinates. And so here I've got my, oops. So that was Cartesian. Here we've got our cylindrical polars. Let's call this phi and Z. And here that means I've got big R as a function of R, big phi as a function of phi, and Z as a function of small z. Okay, now for the spherical symmetric case, it's often easier to use spherical coordinate system, and here we get big R, R, theta of theta, and phi of phi. And in doing so, in explicitly assuming, oops, how does this work? Oops. Here, explicitly assuming this form basically now states that we go from one PDE into three ordinary differential equations with a constraint. Okay, and let's see. Okay, and then the full solution. Okay, now solutions, if you work out these problems in the separation variable, then the solution is simply given by u, x, y, z, which is just a cosine Lx plus b sine Lx. Okay, that's for the x, and then the y is c, again cosine my plus d sine my. This, and finally we get e cosine z plus f sine mz n. And z in such a way that, you know, where L squared plus m squared plus n squared is 0. And here we also note that, you know, in principle, we create a superposition of all allowed values of So Alex is asking, one of them should be the hyperbolic cosine or sine. Yes, but only when you restrict things to this using this constraint. Okay, now since you don't know which one it is, I leave it at this form. It's just easier to remember. Okay, similarly, for the cylindrical polars, we get U, R, phi, Z. This is a little bit more tricky. So here, what we're dealing with is so-called A, and then J, M plus B, Y, M. Okay, that is for the for the R term, and then we get C cosine M phi plus D sine M phi, and then E to the minus kz plus F e to the kz. Okay, again, in this case, there is a sum over this here again, sum over all states, and this J and Yn are solutions to the following equation. So you got x squared plus y plus times x squared times y double prime plus x y prime plus x squared minus a constant v squared y equals 0. Okay, and this is so-called Bessel equation. Okay, and finally, we have the spherical polars, theta phi, and again, did I put the sum here? Yes. And again here for the r, we're dealing with a r to the l plus b e to the minus l plus 1, and we get the regular c cosine phi plus d sine phi l m cosine theta f q plus this, and for all allowed values m and m, l and m, and in this case the m l are so-called genre polynomials. Genre, polynomials which satisfy the following equation: 1 minus x squared y double prime minus 2x plus L plus 1 minus m squared 1 minus m. Okay, so this is a good moment to take a quick break. Again, this is all a lot of recap that we've been doing. So let's take a quick break here. Let's take a 5-minute break. Let's come back at 3:25, and then we'll continue the latter half of the recap, and then we'll look into some advanced stuff. Okay, guys, in a bit. Okay, welcome back. Harry is saying if it's b to the r to the power l minus 1, l 1 plus 1 instead of e, and you're absolutely right. R. Here we go. Okay, let's move on. We have a few more things to recap. Wrong here. Second term should be y only instead of y double prime for the bottom equation. This one. Prime. Any more typos? Okay, well done. If you can follow along, that's excellent. Well done. Okay. So after having looked at this, we looked at what happens to external fields. Right? So if you have materials and there's an external field applied to it, what happens to the field inside this material? And so this is materials. Okay. And here, in particular, we considered there's an external field. Okay. They produce polarization or magnetization. And so what we have instead is the considering an electric field, we rather think about it in terms of a displacement field, and instead of a magnetic field, we think about the auxiliary field. And this here is simply epsilon naught E. P is not a polarization. And similarly for H, we get 1 over mu naught B minus M, where M is the magnetization. Okay. And this is these, no, the introduction of this P and the M lead to surface charge, polarization charge, and a polarization charge density. The divergence of P, the P dotted with the normal to the surface. We got M, this is the surface magnetization, surface current due to the magnetization, M cross M hat. And similarly, we've got the current density due to the magnetization, which is the curl of M. Okay. And then, bringing this together, have the Maxwell's equations in matter is just, it's just the divergence of D is rho F, where F stands for free, so these are the free charges. And the curl of E equals 0 still. We get that the divergence of B equals 0, and we get the curl of H equals the free current. Now there's a special type of material which are typically called linear and homogeneous. Materials. for which we actually have that the polarization is proportional to the electric field through this chi E, or we have M equals chi M, like this, in such a way that D, the displacement field, is just epsilon E and 1 over mu B. Epsilon is just epsilon naught 1 plus chi E and equals 1 plus chi M. Okay, so in this, for these linear materials, we have that the there's now a direct relationship between the displacement field and the electric and the auxiliary field and the magnetic fields, and this simplifies the equations drastically. Now, we can also think about it in terms of the so-called boundary conditions for these. The boundary conditions. So now it's just D2 perpendicular minus D1 perpendicular is sigma F. Again, this is the free surface charge. We get parallel 2, parallel 1, 0, 2, perpendicular B1 perpendicular equals 0, and I got H2, 1. Yes. Okay. So that's for the materials and matter, and even though the theory may not be very difficult, but the questions are typically structured in such a way that you get different materials, and then you really need to start considering things like the boundary conditions. Okay. Now, the last topic that we looked at, and this is where things are starting to get interesting, are of course the time-varying fields. Time-varying fields, and in particular, there's two contributions that are important to this. One is from Faraday, who realized that the curl of E gives rise to a changing magnetic field, or the other way around, a changing magnetic field gives rise to a curl of E, and Maxwell introduced a symmetric case for which the curl of B equals to mu naught epsilon naught partial E partial T. Okay, so in this case, we have that a time-varying magnetic field produces an electric field, and a time-varying electric field produces a magnetic field. And so, with these two additions, we actually end up with a different set of Maxwell's equations, which now states that divergence of E is still rho over epsilon naught, but that the curl of E is, as we've seen before, minus partial B partial T. Similarly, the divergence of B equals to 0, and the curl of B equals to mu naught J plus mu naught epsilon naught partial E partial T. And charge conservation is now given by partial rho partial T plus the divergence of J equals to 0. charge conservation. You can write the same thing in terms of a integral form also. So this is E dot ds equals 1 over epsilon naught rho dv, integral of E dot dl equals now minus integral of dot d dot partial b partial t s and dot ds 0 and dot dl equals mu naught integral e plus from naught partial e partial s. Okay. And again, charge conservation is then given by j dot d minus integral of partial rho partial t. Okay. Now we can even write these in the presence of matter. So in matter, this then becomes the divergence of d is rho free, curl of E minus partial B partial T, curl of B equals 0, curl of H equals to J plus partial D partial T. Okay, so this is the whole set of equations where we talk about time varying field. Now, the interesting thing about the time varying fields is it turns out you can write them of a particular form. So we have the so-called D'Alembertian, box operator, which is just Laplacian minus 1 over c squared partial t squared, so that we can actually write that the box equals to the gradient of rho over epsilon naught plus mu naught partial j partial t, and box B equals minus naught curl of j. Now we can translate this to the potentials. So we box I equals negative rho epsilon naught, box A equals negative mu naught A. Again, have to have specified the divergence of A. In this case, it's minus 1 over c squared partial phi partial t. Okay. So when writing this, this is the so-called wave equation, and so we can actually consider this wave equation in empty space. Actually, you can show that E as half omega I omega t minus k dot r plus coefficients minus I omega t r. Okay, similarly B also write n1/2 omega P3I omega t minus r minus I omega r. Okay. All this is saying is that we can write this as an exponential, where there's a omega, a wave frequency, and k, which is the wave vector, which has both the wavelength and the direction at which the wave is traveling. Okay. In general, these coefficients here are complex numbers, but again, we typically don't worry about the exact forms for this lecture course. Now, having written things like this, we can get a few of the properties of these waves, and in particular, the properties of waves. Here we know that k, this is actually directly from Maxwell's equation, k dot E is 0, and k dot B is 0, which basically means that k is perpendicular to E, is perpendicular to B, but we can see that k plus E plus omega B, and cross B equals minus omega over c squared E. So what we learned from this is that k is perpendicular to E, is perpendicular to B, or in other words, k is parallel to E cross B, and that the amplitude of the B field is just 1 over c of the E field. Okay, so that's pretty much in in lecture and in an hour and a bit everything that we've covered in terms of electromagnetism. Okay, so Maxwell's equations, applications, how to solve it, and then time, putting them in matter, time varying fields, derive Maxwell's equations, and again, look at their solutions. Okay, so I suggest that we take a quick break, again, 5-minute break, and then we'll come back to, take a start about some of the advanced topics that we that you may see in 4041, but also in going forward in other courses. Let's come back at 3:50. 6 minutes break. See you guys soon. Bye bye. Okay, welcome back. Let's take a look at the remainder of this lecture. Let's take a look forward. Let's see what are things up in the immediate horizons. I have two kind of sets of things that I think are worth talking about. One is what are the immediate kind of next advanced things that you can do within the topics that you guys have covered, and also on how to even go forward in terms of the theory, advanced topics. Okay. So the first one I wanted to highlight is so-called Green's functions. I don't know whether you have seen these before in some of the mathematical courses, mathematical physics courses you've taken, but one way to solve partial differential equations are actually using so-called Green's functions, and they make your life, much. I wouldn't say simpler, but it's a very straightforward recipe. It's quite advanced, but it's a straightforward recipe. And the principle is actually rather elegant, rather simple. So imagine that we got a differential operator, let's call it L, and we act upon it on some f, right, which is, let's say, a function of r. And that gives us back g as a function of r. Okay? So imagine L being, let's say, the Laplacian, and then a Laplacian operating on a scalar potential gives you the source term. Right? That's basically what this equation says. Now, that is, this is a very general statement about, kind of a differential equation. But if we assume, in this case, where L is a linear operator, now, the trick here is to take this L, but instead of solving this equation that we see here, we actually solve LG. This actually depends on R and R prime, and I'll explain exactly what these mean. And the answer is a delta function, R minus R prime. Okay. Again, R and R prime are typically, when we think about the situation, is typically the R is just the location where we're interested in the field, and R prime is the location of the element that we're considering. But in general, this equation here, where G in this case is the so-called Green's function. The Green's function is once operated on the Green's function by your differential operator, gives you back the delta function. And why is this such an important function to get? Well, this is the equation that we wish to solve, but assume that we're able to solve this equation. In that case, I can write down that f is the integral of big G, small g. Maybe it's easier if I write down the explicit dependencies. So g is a function of r prime, and b as a function of r prime, d prime. And f in this case, f is a function of r. Right, so once I found g, I can just do the integral on the right-hand side to find f. So as long as I find, for any differential operator, I find the Green's function, which satisfies this equation, I can always end up constructing this f given my source term, g. Now, just to convince you, indeed, if I apply L on both sides, I get L over the integral g small g dv prime. So because it's a differential operator, I can put it inside the integral. This L here, in this case, only operates on G because it only operates on R, right? This here only operates on in the coordinate system of R, not R prime. So it can only operate on G, not on small g. So in which case we get LG like this, G. And as you can see, LG is just a delta function. It's delta R minus R prime, prime, which is equals to we're looking for G. The function of R. Right? So I don't need to do a lot of effort in the sense of thinking. As long as I find the Green's function, I'm able to solve this integral here, and I get it. Right? If I know G, whereas G is typically the source, right? It's the charge distribution. This is a very elegant method, but of course the trick here is to find the Green's function, and that's a whole different theme within mathematics, is to find these Green's functions for different differential operators. And I'm not going to go into the scope of this, but one Green's function, if we let L being again the Laplacian, and the Laplacian of G was delta R minus R prime. And actually, this is something that we have seen before. It's just 1 over 4 pi 1 over R minus R prime, like this. So we've more or less kind of been using the differential, the Green's function, but without explicitly telling you that we have done so. Because if you recall this expression for phi, this expression for phi is indeed the solution to this equation over here. Right? And so rho is then G, small g, big G is just R minus R prime. So 1 over R minus R prime. So this here is more or less the Green's method, Green's function method. But in general, the trick is to find the Green's functions. Okay, again, we're not going to go into detail. The other thing I wanted to that you will see next in 4041 is the concepts of energy and momentum associated with the field. This is really the energy and momentum of the electromagnetic field. And again, here, maybe the simplest way to think about it is, imagine the following equation that we've more or less seen before, right? So this is rho, and I'm just going to label this with a nu. So any, and this is not necessarily just charge, but anything, any quantity that you can consider. It could be charge, could be other things, but any density that you can consider, the rate of change of anything is balanced, or balanced by the flux of this thing. And that should equal to, let's say, any particular source term. Okay. So we've seen it before where we have the conservation charge. So there's no source term. There's no, you can't suddenly create extra charge, right? You have to bring it in from somewhere. In which case this is 0. But of course, if you were able to produce something out of nothing, you have this extra term here. But otherwise, this is simply a generalization of the conservation of charge. But this works for everything. Now, what you can show, you can actually delve deeper into Maxwell's equation. And it turns out you can write things in the following way. You write partial by partial t of a half epsilon naught e squared plus a half 1 over mu naught b squared plus the divergence of 1 over mu naught cross b equals to j dotted with e. And so, indeed, when you write it like this, you can start to consider that this is a still. Oh dear. Okay, it's still visible. Sorry, the internet is a little unstable. Okay. So if you can write Maxwell's equations, you can derive this equation over here. And this pretty much gives us an equation that tells us about the energy. So the energy density, the flow of energy, and then a source term like this. And so we can, by rewriting things like this, we can actually identify that the energy density is indeed a half epsilon naught e squared plus 1 over 2, 1 over mu naught e squared, which is the energy density, but also the flow of the energy, so the flux of the energy, which is 1 over mu naught cross b. This is actually the so-called Poynting vector, which is just the flux of energy density. Okay. Similarly, we can do this for the momentum. So we can end up also writing partial p partial t plus the divergence of t, and I'll define these in a moment. You got minus rho e minus j cross b, and again from Maxwell's equations. But here the important thing to note is that this is now the so-called momentum density. It's just mu naught cross b. This is the momentum density. So again, so this is really where, in the next course, you'll really work with the concepts of energy and momentum densities. Okay, there's another thing that you will explore to much greater depths, but I've actually left a little hint for you in the last problem set that will be released today. And that is what happens when you have dissipation of waves. So when you have waves traveling in media, you can actually have a dissipative term as well, right? So we consider typically waves in free space where there's no attenuation. The wave keeps traveling. But when you have waves traveling in a medium, what happens is that there's dispersion. There is a particular attenuation term as well. And so you'll explore that in the last problem set. It's very abstract, but you get the first glimpse of seeing something along that form where you're calculating the quality factor of a particular material. So those are typically the topics that you'll end up in a more advanced course on electromagnetism. You'll see things like waveguides, and again, it's just how do waves travel in more complex situations rather than just a free space. So that's in terms of what you can expect immediately in the next electromagnetic theory course. What I also want to do is give you two handles to think about what are the extensions to these theories. And so again, the first one is special relativity. This is again a hugely influential theory from Einstein, and I think most of you know this theory in a rather limited sense, typically in the consideration of a so-called Lorentz transformation. Okay. So suppose there's some velocity x direction. So this is simply typically written as t prime. So this is the word prime is one coordinate system, or sorry, one observer, which is the either the moving or the non-moving observer, and can relate the two different observers and their times using the following formula: x prime equals gamma x minus b c t, and y prime equals y and z prime equals z. In which case gamma is 1 over 1 minus beta squared, where beta is just v over c. Okay, so this is usually what people at this level have seen from special relativity. Great if you've seen more, absolutely, right? That's not the point, but two important results are coming out. So this so-called length contraction. So when you're traveling with a particular velocity, or when you see something traveling with a particular velocity, the length will have been contracted, or it seems shorter compared to when you're stationary next to that object. Okay? The same as time dilation, where time is where time runs differently depending on whether you're a moving observer or not, at least in comparison to someone who's stationary. So that's all encapsulated in these equations. Now, how does it actually matter in terms of what we do in electromagnetism, right? We don't typically see things that are that high velocity that it actually makes a difference. But that's not necessarily true. And this is something that I remember the first time I saw this. And this was in I think in the second year. And this was the first class of electromagnetism in the second year. And the guy, no, sorry, third year, I think it's third year. The guy stands there and goes, okay, magnetic fields don't exist. Right? So that grabs your attention. You're like, okay, what's going on? It's like, I'll show you, I'll prove to you that magnetic fields don't actually exist. So mind blown. Okay, so I'll give you a quick demonstration. I won't go into the extensive maths, but I'll give you a quick demonstration of what he meant with magnetic fields don't actually exist. Okay, so imagine the following. Imagine that I've got a pipe or a wire, and I've got some negative charges here, and I've got some positive charges here. Okay, and I'm letting the negative charge, move in one direction. So in this case, I have no net charge density, right? And it's just equal number of plus and minus. But I do have there is a charge. Sorry, there's a current. Okay? So there's a current flow. Now imagine I've got a positive charge here. Now, in this situation, right, what happens to this charge? Nothing. Right? There is, yes, there is a flow, there's a current, but since this charge is stationary, nothing happens. But that is different when there is a when I set this to moving. Let's just, for the ease of use, just set these to be equal. Because now I have a F plus QVB. Right? So this current here produces a magnetic field, and I've got a charge that is moving, and so I get a force that should push it away. Now this is a relatively straightforward scenario, but now the thing is, I can transform this instead into the following scenario. So instead of this scenario, I now have an observer that moves along with this positive charge. So from that observer's perspective, this charge is stationary because it has the same velocity as the negative charges. The negative charges are stationary. But now the positive charges are moving. Okay? I'm moving the opposite direction. But because this positive charge is not moving anymore, nothing happens. Even though in this scenario, the charge gets pushed away. Well, this apparent discrepancy is, and I say it's an apparent discrepancy because what happens here is that because I am, instead of here in a frame where I see this plus charge moving, I'm now here in a frame where this charge is not moving. So I, as the observer, have a particular velocity. So what happens with this scenario is that because I'm moving along with this field, this here, plus charges, the distance between them will have been length contracted. And so what is here now is that there's actually there's now actually a charge density, a net charge density, simply due to length contraction. And so in this case, what I have is F equals Q E. Right? So it seems like an electric force. This seems like a magnetic force. You see the difference, right? So depending on which observer, it could actually be something that we think is due to a magnetic field, or it could be something that we think is due to an electric field. And the conclusion from this is fairly straightforward, right? So, the E field are observer dependent. So a B field is nothing but an effect that you see, is nothing but the electric field for a different observer. And for me, mind blown when I first saw this. Right? In principle, there's no need for a magnetic field. Just go into the right observer frame, and you have an electric field. Mind blown. Okay, how does this work in general? Okay. One way to kind of see where this may lead, again, we're not going through the full derivation, but in the okay, so Manchum is asking, sorry, could you repeat what frame is for E field. So this frame here, right? Because the charge is not moving. Plus charge is not moving, right? I'm moving along with the charge. So from my perspective, the plus charge is not moving. So there cannot be a magnetic force because the charge isn't moving, right? Because V is QVB. But in this frame, the charge should still go, right? It's not possible that in this frame I see the charge being repelled, and then in this frame I don't see the same. I don't see any repelling. But what happens in this frame is because I am moving with a particular velocity. I'm the observer. I'm moving with a particular velocity. This, the positive row, actually the distance between them gets length contracted. You end up with a net charge density, and the force then actually appears to be an electric force as opposed to a magnetic force. And so the interaction here that causes this charge to be repelled is an electric. That is due to an electric field, not due to the magnetic field. Does that answer your question, Manchu? Right. Same here. Okay. Mind blown. That was my reaction as well. Imagine this is your first lesson, first lecture. You're sitting there. You're like, okay, everything that I've learned in the last 2 years, I could just throw it out. I remember going back to my fridge and a magnet. Like, no, there's a magnetic field. Right? There's a magnet. I hold it in my hand. Again, when we talk about special relativity, this is something that will become more clear. But what is the root to considering special relativity, and how is this baked into, right? Because this effect is completely baked into electromagnetism. Don't have to do anything. It is already within my framework. Well, how can this be seen? So imagine that I define a new object. For those who are interested, this is called a 4 vector, and here I'm grouping together time, x, y, and z. Okay. Now, if I do this, then I can write for the Lorentz transformation that I've written down here. I can write it in a very compact form. So x mu, I'll put a prime here, is simply a transformation matrix x mu. In such a way, what do I mean by this? And that is just that t prime, y prime, x prime, y prime, z prime is a 4 vector, gamma minus gamma beta minus gamma beta gamma 1 1 0 0 0 0 0 0 0. I have a transformation matrix here. Let me make some space for myself. Okay. And here I've got t, x, y, z. Right? So grouping this together, I can go from one frame to another using the so-called Lorentz. This is a transformation matrix. And it turns out that this transformation matrix is going to be important, but it turns out we can actually introduce the same structure of grouping together one scalar, time is just a scalar, and one vector, which is the position. And how do I do that? Well, remember this equation over here. I've got box phi equals rho over epsilon naught, and I've got box A equals mu naught J. Okay, I've got one scalar and I got one vector. Well, I can end up introducing the following equation like this, where A equals phi, comma A equals rho, comma equals B. Okay, by grouping together the scalar potential and the vector potential into one object, we call for potential, and we have the introduction of a for current, which is just the charge density and the current, we end up with an equation like this, which actually turns out is fully relativistic. So it is actually really beautiful, right? In Maxwell's theory, we didn't have to do anything extra, and yet we still get a very simple, straightforward way of writing down the formula, the theory in such a way that it actually is compatible with special relativity. In other words, as the example before shown here as well, the notion that, the notion of special relativity is completely baked into this theory. And it is exactly that when I go from one frame to another, right? You see it here as well, this one, right? When I go from one observer to the other, I'm starting to mix the time and space, right? So this new time is both time and space, is a mixing. And similarly, when I go from one observer to another, I'm starting to mix not just the scalar potential, but I end up mixing the scalar potential and the vector potential. And we had seen this before, right? We've actually seen this before, where when I'm looking at the time varying fields, I actually end up with a choice of that E, this here, E is actually minus the gradient of phi plus the time derivative of A. And so you end up mixing things, and it's the same here. Because I can write this equation in this way, I end up, when I'm doing a transformation, right, when I'm going at a particular velocity, when I'm going into a different observer, I end up mixing the scalar field and the vector fields. Sorry, scalar potential and the vector potential. Therefore, I'm mixing the E field with the B fields. That's how special relativity seeps into it. And that's why there's such an intimate link between electromagnetism and special relativity. In fact, Einstein's inspiration is basically thinking about light. Why, what happens if I travel at the speed of light? And it also makes sense now, right? Why is the speed of light? Why does that have anything to do with, space? Why can you not travel faster than the speed of light? I mean, I can imagine why light cannot travel faster than the speed of light. Why can anything not travel faster than the speed of light? So the theories are very intimately connected, and that's really, it's a beautiful aspect of this electromagnetism, where special relativity just comes rolling out. It's beautiful. Okay, the final thing I want to discuss, we're a little over time, so bear with me. Again, all of this is not part of the syllabus, right? So you don't have to worry about doing special relativity calculations. The other thing I wanted to at least give you a sense, a notion of where things may be headed is so-called quantum electrodynamics. And this is just the quantum theory. This is quantum electrodynamics. Okay, QED. And again, we're nowhere near at the position of being able to do this, but still, I want to give you one or two kind of hints that may point you to the right direction. And that makes it plausible, makes it feasible that this is something that you can do. So imagine the following, right? Imagine we've got classical mechanics. where the Lagrangian is given by t, which is a function of x dot, minus v, which is a function of x. And then we write down the Euler-Lagrange equation by dt of partial by partial x dot of the Lagrangian equals to 0. In this case, the Lagrangian is just a half mx dot squared minus v x, right? We're in the particular potential. Now, when I'm considering a charged particle, so this is just a free particle, and I'm looking at a charged particle, it turns out that I get a half mx dot squared minus q phi plus q a x dot. So this here is more or less just the, the electric potential, right, or the potential energy due to a charge. This here is more or less kind of the magnetic field force, or at least the source for magnetic field source. Right? And so this is for a charged particle. And so yeah. Now similarly, I could, this is a little bit detailed, but I can also write the Hamiltonian for charged particle being P minus QA. P is the momentum, 2m plus Q phi. Okay. Now, this by itself is purely classical. Now, how do we take the next step? How do we take the leap to quantum theory? Well, recall that in quantum theory, this is something that I think most of you are doing right now. I think it's 3021. Wrong, but it's one of those numbers where in quantum mechanics we make the realization that x becomes an operator, right, and also that p, the momentum, becomes an operator p, such a way that I h bar gradient, and these form a pair in such a way that there's a commutation relationship between this. Right? Okay. So now, how do we take the step to quantizing the electromagnetic field? Well, consider the vector potential, and I'm actually going to write this now in Fourier space. This is just components of the Fourier. So a k I k r. This is a general function of t plus a k. This is minus 1 e to the I minus I k dot r. Okay. So again, I write this as more or less this is not exactly a wave, this is a solution to the Klein-Borden equation instead, but what we do have here is almost like a Fourier transform of the vector potential. Okay. So these are just the coefficients multiplying some e to the I k r. And the way to, or one way, I wouldn't say the way, one way to end up quantizing this is to assign these AKs into so-called, let's put a bar on top, it's easier to recognize, to assign an operator here to omega v. V is the potential again, epsilon naught a hat. Right? Similarly, a then goes into an operator to omega v epsilon naught. I need to check whether these are actually correct, but that's fine. A hat dagger. Okay, and again, these have their own commutation relationships. A dagger, also a delta function. Okay, k and I don't want to really spell out the details either. Right, and so this is kind of this is the route to which you end up also doing quantization of the electromagnetic field. And that also happens through the vector potential, which, as you can see, right, the momentum is, for example, supplemented with the vector potential here. And we can end up quantizing it in the form like this, in a similar way to which you're quantizing the x and the p. Okay, I've already gone over a little too much. I apologize, but I wanted to give you at least kind of, a half a step towards some of the exciting new things that you get in either next term or in the coming 2 or 3 terms that you have left. I don't think you'll end up doing quantum field theory. I don't think we actually offer this in the undergraduate, but that's in years to come. Okay, this ends the entire lecture series. I hope you've enjoyed it. I hope despite maybe the kind of the amount of work that you have to do, I hope you found this theory to be an enlightening theory, at least put in a way where you kind of feel like, okay, some of the mathematics you had done in the past 2-3 years are finally paying off, right? You're finally using more advanced tools, and you're finally learning to give a systematic explanation to fields. And that's really been my perspective. Like, why do I teach this course in this particular way? Is for you to really understand how to, how to step away from thinking about things in terms of forces, and think about it in terms of fields. Okay? That's really the more fundamental aspect. As I was saying here, when you go into quantum electrodynamics, you end up really needing to adopt that view. Okay, thank you very much, everyone. As I was saying, I'll aim to have the remainder of the lecture notes published next week, or at least by next week, so that you can use that for your revision. We have one last problem set, which is will be released at 5 o'clock today, and that is a little bit kind of refreshing your things about waves, but we won't talk too much about waves in the actual in the actual exam either. Feel free, if you have questions, if you're revising, you have questions, to post them on the discussion board. That way everyone can see it. I prefer not to get private emails or emails. It's just easier to put everything out in the open. Everyone can learn alongside. But still, if you want to email us, that's fine as well. Other than that, I think the only thing I really have left to say is, well, thank you for listening. I apologize this is done over Zoom. I'd much rather see everyone in person. But good luck with the exam. I won't make it a very difficult one, I promise. At least hopefully it's going to be an interesting one. It's really one where you can test your knowledge, and best of luck with revising. Okay, feel free to stick around to ask questions. Otherwise, thank you very much. And I will also circulate very soon the procedure, the details of the final. Bye-bye, everyone. No, thank you, Harry. It's been very impressive to see you spot all my negative sides and stuff. Why is there no negative, no length contraction? Okay, so length contraction is really with respect to what, right? So that's fine. There's no absolute thing called length contraction. Here, what my starting situation is that I am in a frame, right? I'm in a frame where the density here lines up. The negative and the positive, the spacing between them are exactly the same. That's a starting assumption, in such a way that I make a situation where there's no electric field. But once I go from this situation to this situation, I am doing a transformation, right? I'm moving with a particular velocity in such a way that these then remain stationary, but these will have acquired, a velocity. So I am going in a particular velocity, and these things are now moving in this particular direction, and you getting the length contraction as dictated by the Lorentz transformation. So it's really more just a choice um, of frames, right? So it's really just a starting condition. Oh, my pleasure, my pleasure. As long as people find them useful, as opposed to just reading your book, then that's my job done. Uh, I also appreciate some people just like to sit down and read their own book. That's fine for me. So I try to give my lectures at least in a way that it may prove helpful for students. But thank you very much for coming. Okay, I don't see any other more questions. Let me turn off the recording. And Pearl,